And this is the start of the ocean uncertainty quantification session on Wednesday, September 23rd. And I will again thank the co-leads, Kimberly Baldry, Regina Easley, Donata Tiglio, and Christoph Waldeman for helping us put this session together. This is the third of 3 sessions. And our first speaker this morning is Rick Lumpkin, who manages AOML's component of NOAA's Global Drifter Program. And it's part of an international effort to maintain a global network of surf and drifting buoys for climate and weather research. Rick also serves as co-chair for North America on the executive panel of the Data Buoy Cooperation Panel, a group that I have quite a lot of respect for, and actually have the pleasure of giving a presentation at their Science and Technology meeting coming up at the next meeting of DBCP. So Rick, you should be able to share your screen and take it away.
Great, thank you very much, Mark. Let me do that now. And can you confirm that you see it?
Yes.
Great. All right, I will be talking about evolving uncertainties in Global Drifter Program data. And for this particular talk, I'm going to focus on the location and velocity. Although I'll make the point at the end that this is not just the component of the program, it has changed through time. Quick overview of the program. The objectives are to maintain an open ocean array of something like 1,300 drifting buoys to measure a number of different parameters and to provide a data processing system for the use of the data. This is both for operational purposes, such as weather forecasts and ocean state estimation, and also then for scientific research and delayed mode. We produce quality controlled data, which should be climate quality.
Excuse me, Rick.
Yes.
Can you speak a little closer to your laptop? You're fading in and out.
Absolutely. Is this better?
Yes.
Great. Okay. So the program is organized in 2 components: the Global Drifter Center that I manage, which maintains the global array, quality controls the data, and produces delayed mode products and data, and the component at Scripps, which for many years was run by Peter Neeler and now by Lucas Anturioni, which supervises the industry, upgrades the technology, and manages the Iridium data stream. Brief history of the program. The instruments, a number of different types of drifting buoys had been deployed through the 1970s as Service Argos allowed for satellite tracking worldwide. And the Global Drifter program evolved in the 1980s from several regional efforts to measure currents and temperature. The design was consolidated in the Surface Velocity program of the World Ocean Circulation Experiment in the 1980s. From the late 1980s to the late 1990s, it evolved from an array primarily looking at El Nino oscillations in the tropical Pacific to other regions around the world to finally global observations. In the OceanObs 99 meeting, the goal was set to have this program become a 5 by 5 degree of array, basically something like 1,250 drifters. And this goal was met with the deployment of the 1,250th drifter of the array in September 2005. And approximately maintained since then at something like this size. There are a number of standards which have not evolved through time that basically we try to maintain to keep a homogeneous data set. For example, you see the schematic of the instrument at the left here with a surface float connected by a tether to a Holy Sock drogue beneath the surface. This Holy Sock design minimizes the impact of wind and waves while remaining easy to deploy, easy to fold up and then toss into the ocean. And the drag area ratio, which is the cross-sectional area of the drogue to the cross-sectional area of all other components, is 40:1. And this is something that we do not change, with the drogue centered at 15 meters depth. That 40:1 ratio has guaranteed that the effect of direct wind forcing and waves at the surface is less than a centimeter per second and 10 meters per second of wind. This has been measured by an ADCP attached to the instrument. The surface float is a sphere to minimize wave rectification. And the velocity of the instrument is provided by the change in location over time. Now, if that tether breaks, and it eventually does for most drifters after an average of something like 300 days in the water, the instrument itself tends to live like 450 days or longer, then the error is much larger, for the velocity, because now you have a downwind motion superimposed on the motion at 15 meters. And that downwind motion has been estimated to be something like 1% to 3% of the wind speed, which also would include wave effects and other things like that. But not everything has remained the same through time. There have been changes, and these changes affect the errors that you would assume are in these velocity measurements. For example, there was an instrument redesign in the late 1990s, primarily to decrease costs. You see the new design on the right. Now, the standards have been kept here, centered at 15 meters, 40-to-1 drag area ratio. But the instrument cost went from $5,000 for the original to something like $1,500 for the mini, and shipping costs obviously went down considerably as well. It basically was what was needed to be able to reach that OBS 99 goal. And it was phased in the early 2000s. Another major change that's happened is the satellite positions. We started off using Service Argos, which was available in the 1970s. And early on, a lot of drifters were on 1 day and off 2 days, a duty cycle to extend their lifetime. But this was phased out by 2000 as the ability to transmit the data primarily was made more efficient, so that the drifter could, still with just a pack of alkaline batteries, live that 450-day lifespan on average. Also, the Argos constellation grew over time, so more satellite fixes were provided. And in 2005, we switched to multi-satellite processing. Effectively, the Argos satellite figures out the position from the redshift, blue shift of the instrument as the satellite passes overhead. And Argos charged considerably more money to receive all of these location fixes. And basically NOAA was not able to cover that cost on top of all the other things it wanted to do. So we got only a subset of the fixes until 2005, when, to try to remain competitive, Argos offered all of those fixes for the same price. And suddenly we received more fixes for these drifters. Finally, there was a transition to Iridium plus GPS that I'll talk about in a slide or two, which provided much higher quality locations. And finally, there's a change in how drogue detection was done, which I will talk about later in this talk. All right, so here you see a plot of the mean time between GDP location fixes, average across all drifters at any point in time. And you see from 1990 to 2005, this kind of general decrease in the spacing between them. This is because of both the growth of the Argos constellation and the decreasing number of drifters that are 1/3 duty cycle, more and more of them transmitting every 90 seconds and just hoping that a Argos satellite would pass overhead. And you see that they did, kind of from 6 to 7 hours on average down to about 3 hours on average. Then the switch to multi-satellite processing dropped us down to less than 2 hours between, on average, by the time we started phasing in the Iridium and GPS drifters. That switch from Service Argos to Iridium was primarily driven by cost savings. It was much, much cheaper to get the Iridium fixes according to the deal that was negotiated at that point. And so by around 2014, the decision was made to very aggressively phase in Iridium by basically stopping the manufacture of drifter using Argos and 100% manufacturing Iridium drifters. So as the Argos drifters in the array aged and died, the fraction of the global drifter array using Iridium increased very rapidly, starting in around mid-2016. With Iridium plus GPS, we get on-the-hour locations more frequently if we want, for example, drifters deployed in front of hurricanes, and very high accuracy. Service Argos locations are generally on the order of several hundred meters error. They can be quite larger in some cases, whereas GPS is on the order of a few meters accuracy generally in the field. Now, the interpolation of these data to regular 6-hourly intervals has been done for many years, starting in the 1980s, for a quality-controlled data set. And that interval, 6 hours, was chosen out of necessity. This is sort of the frequency we were getting observations. And obviously, this is aimed at sort of large-scale, climate-scale studies that for which 6-hourly is perfectly fine. In other words, not looking at inertial oscillations or diurnal or tidal, but rather, low-frequency, large-scale shifts. And the interpolation algorithm, this kriging, is described in Hansen and Poulin in 1996. Now what that provides is error estimates for each location. And when you interpolate through a gap, the error bars will naturally grow through that gap. And here's a fine example here. This drifter had a large gap from the area over here to the area over here, during which the formal errors given by this routine and distributed in our 6-hourly data set reflect this large growth. This particular example looks like it may have been a 1/3 duty cycle as well. You can see that very clearly in the error estimates for the longitude and the latitude, kind of a pulsing 2 days, large errors, 1 day, small errors, as the interpolation is passing through that 2-day gap to the 1 day on again. Surface Argos provides a location class to tell you how big the errors are for every individual fix. It's an estimate, effectively. The classes 0, 1, 2, and 3. And Surface Argos had basically said, look, the errors are for class 3, less than 250 meters. So that's the highest quality class you get with Surface Argos, all the way up to class 0, which was not used for the 6-hourly interpolation, which is a greater than 1,500 meter error. So class 1s, 2s, and 3s were used in that creating algorithm, but what was not used was the error information for these individual fixes in that algorithm, which is unfortunate because that's information lost. That routine basically used sort of an average error for class 1, 2, and 3, weighted by the number of these type of fixes that were received. So this was reevaluated in a paper led by Chanelli Pope, who's in the room here with us, published in 2016. Looking at drifters that both were using Argos and had GPS on board. So if we use the GPS as truth, we can look at the errors for class 1s, class 2s, and class 3s. You see from the paper, the figure on the right showing those. And as it turned out, the numbers match fairly well with what Surface Argos had given as those estimates. So that was good to see, but the distributions were not Gaussian. And so that meant that more advanced routines for doing interpolation at higher frequency was appropriate. And in the end, Shen decided to go with a weighted maximum likelihood estimator to provide errors for the locations at hourly intervals for these Surface Argos positions, and using the location class information as well. And you see an example from the hourly data set that's now hosted at the Global Drifter Program in this plot here for one particular drifter. So I want to conclude the talk with an example of an evolving best practice that comes from errors in the data that we became aware of. Effectively, around 2009, Semyon Grosky approached me and said, I'm seeing something very weird for drifters in the Antarctic circumpolar current. They have very large speeds here, in like 60 to 40 south, compared to independent estimates like Oscar and Soda, almost twice as large. And when you look at time variations, and this is something that Marie-Hélène Rio also approached me later in 2009 with concern about, there's this very large spurious looking fluctuation starting in around 2004, growing far beyond what had been seen if you average all the drifters from 40 to 60 south at earlier times. And these fluctuations seem to have nothing to do with things like the southern annular mode. What you see in this plot is actually removing the geostrophic component using altimetry and a mean dynamic topography. So this should be the ageostrophic component of all the drifters averaged in this band. And you see these very large velocities that are reached in 2006 to 2008, and they remain anomalously high thereafter. They're not as high. Well, this was extremely problematic. And one of the things that I basically lost some sleep about almost immediately is that this happened about the time when those mini drifters were phased into the array. So my immediate hypothesis I needed to test was, is this because of that phase-in of this new design that we thought was going to move just like the older drifters? And happily, that's not the case. The data set is homogeneous as far as we can tell from that design change. One of the ways you can see that very clearly is, in addition to in situ measurements that were done by Peter Mueller in calmer regimes in the Southern Ocean, is you can just do this sort of calculation for the original drifters in light gray at the top versus the mini drifters in medium gray in the ACC region. They're not identical because of differences in where they're sampling, but you see this kind of spurious growth for the original drifters, ignoring the phase-in of the Mini design. So that's not what's happening here. It's something else. When you, again, look at, for example, automatically eliminating drifters that start moving anomalously rapidly downwind as another indicator of when the drogue was lost, you go from the dark curve in the bottom plot with that anomalous trend to the light curve. So what this indicates is that we were missing drogue loss in the data. And as it turned out, here's the reason why. So the drifters for all those years from the beginning of the program had used a submergence sensor for us to know when the drogue was lost. When the drogue is attached, the surface float gets pulled underwater very frequently. In fact, it spends more time underwater than at the surface. And then once the drogue is lost, it spends most of its time floating at the surface. So here is an example of what was happening as we started kind of moving into this bad period of time when the drifters started becoming harder and harder to read. The sensor became very noisy after a while in the water. You can see in this particular example, after about 400 days, it becomes much noisier than it had been from deployment. I put a big solid question mark there. And then there is a rapid drop-off many years later in the data, or 3 years later in this particular case. The Drifter Data Assembly Center at AOML was aware that the sensors, particularly for one manufacturer, had become much noisier. And unfortunately, this one manufacturer was the one with the best barometers, the highest quality barometers, and thus were the ones that were primarily and preferentially deployed in the Southern Ocean, where these signals are very strong, as well as in the North Atlantic and North Pacific. The manufacturer's advice was that we should read drogue off when the sensor does drop abruptly, as seen in 9 February 2003 for this example. There are many other examples like this, however, and as it turns out, the drogue was actually lost earlier, as you can find out when you look at other issues. So what had happened was that manufacturer had done subtle, unannounced changes in the design of the submergence sensor, moving the two probes for which you look for a connection because of the conductivity of salt water, moving those closer together to a point where a salt bridge could form, for example, if the surface float is floating high in the water. This caused a misdiagnosis in a lot of these data. And these communications unfortunately concealed this problem for quite a while until researchers brought it to our attention. We tackled the problem finally and corrected the data set. We did this by looking at other indicators as well, change in transmission frequency. When the surface float is no longer pulled underwater frequently, the variations of frequency become larger, and we look for that sudden increase in anomalous downwind motion. So we fixed the data after the fact, corrected it in 2013, and issued a new best practice. We switched from tether strain from submergence to tether strains. The recommendation was made at the Data Buoy Cooperation Panel Best Practices Group that this switch should be done for all manufacturers. Once we introduced GPS to the drifters, we also found that time to first fix was a robust indicator. It takes a lot longer to get a GPS fix when you're pulled underwater frequently by the drogue. So, in conclusion, drifter locations and thus velocity have evolved generally to be more precise and to be more frequent as you go through history. And error estimates should reflect this, as done in the Elipo et al. Paper. Changes in instrument design will happen. This is going to be driven by cost savings, both intentional cost savings, like the switch to the mini drifter, and cost savings that we may not be aware of, like when a manufacturer changes things to make issues a little easier and faster for them, but we're not aware of those, such as the submergence sensor. This means that best practices must be reevaluated periodically. And finally, I focused on location and velocity, but a similar talk could be given for other measurements. A great example is sea surface temperature. The accuracy has been increased due to needs of the satellite CalVal community. So I'll conclude showing the references that I have mentioned during the talk, and I'm happy to take any questions.
Thanks very much, Rick. Interesting stuff, particularly since I was so engaged in it in my previous life. Are there any questions for Rick from the group? Rick, I have one. I'm sure that it's almost a trivial exercise to do a theoretical uncertainty just based on simple accuracy of GPS fixes. Is that the case? And eliminating all of the other factors that go on with a drifter, and imagine that would be an unrealistically high or unrealistically low uncertainty.
So you're referring strictly to the drifters that do have GPS attached?
Yeah.
Or to use GPS? Yes, you could definitely derive. The ways of doing this are to either actually look at a drifter which is sitting stationary and look at the kind of variations that you end up seeing in practice due to the occasional bad fixes. You can then reevaluate that by applying some routines for how you identify the outliers and remove those. And then in the field itself, yes, you have to kind of go more to theory, because it's harder to get a fix, particularly from a drifter that has a drogue attached. And once the drogue is lost, you get much more frequent or much cleaner fixes because you have a very rapid time to first fix. What we did to do this, I didn't mention it in Elipo et al. 2016. I really emphasized more the Argos fixes and how it handled that, but we also did evaluate the GPS fixes. And the errors are generally smaller than kind of the representation errors for what's happening from the hour to hour positions, with some exceptions. And those are drifters that have issues with their GPS and are basically obtaining very noisy fixes. You see examples with very large and frequent outliers, and with such a spread of outliers that is not obvious which ones are outliers and which ones aren't. You have to kind of draw an arbitrary line for some drifters. So the answer really depends from one drifter to the next on what the actual error is in those GPS fixes. One thing we do know, and it would be interesting to include down the road, as I mentioned, the accuracy does get quite a bit better when the drogue is lost. And so there's additional uncertainty information that we're not yet using when we generate these hourly fixes, but it would be an interesting thing to kind of consider down the road.
This Christoph, I would have a question to you, Rick. So yes. You mentioned that your community has been organized from national activities to international, to global network. So I wonder whether you have you're using common QA/QC procedures to process your data, or how do you deal with it? Are you similar organized like Argo with these very strict QA/QC procedures? How does it work?
Yeah, the way we've done this is, the Hansen and Poulin methodology was developed in-house at AOML, but they were very active with the DBCP community, made sure that people were aware of what was done, and then published that in the peer-reviewed literature. I think that as we have moved forward, we have made sure to stay tuned with the international community through those exact same sorts of routes. So the hourly routine that Shen developed, for example, the Data Assembly Center at Heitsenrether requested that code and received it from Shen, to be able to follow exactly what was published in that peer-reviewed paper describing the routines done for that hourly interpolation. So these routines are shared. They're used by more than just the Data Assembly Center at AOML, and that's effectively the pathway that we use. And as we were developing them, we were also advertising this at the Data Buoy Cooperation Panel meeting, which is how Heitsenrether became aware of it before the publication appeared.
Thank you, Rick.
I think it might be important to note that it's all of the data collected from these buoys goes through the AOML processing, so it's definitely consistent.
That's correct. That's absolutely right. So for example, we have not changed the 6-hourly routine, the Hansen and Poulin routine, so that we have a homogeneous data set as far as the processing and quality control goes. But through time, the quality has generally increased, and so that's just something to be aware of when you're looking at these data. That you have this 6-hourly data set with homogeneous application, but and we fixed problems like that drogue detection issue once we found that out. So it's as homogeneous as is practicable for a data set for which the satellite fixes and the technology has evolved.
Other questions?
I have a quick comment, if I may. Yeah. I think it's interesting, and I'm trying to echo the talks that we heard in the past days. You know, at some point, Rick mentioned that the undrogued drifters have different types of errors. So, you know, Rick talked about, you know, the errors that you need to take into account when you're deriving position and velocity based on the satellite positioning. So that's one type of error. And then, you know, when a drifter becomes undrogued, you basically don't have the drogue anymore, and it's just a buoy at the surface. And then, you know, yes, the behavior of the undrogued and drogued drifters, you know, if you're looking at large scale patterns of ocean currents, are very similar, but then there are some differences that are due to the type of oceanic variability that the undrogued drifters are seeing that the drogued drifters are not seeing. So this is what Kyla talked about yesterday, when oceanic variability is masquerading as an error or an uncertainty, because maybe we're not so sure. Actually, you may have a lot of Stokes drift captured by the undrogued drifters. You have a direct action of the wind on the buoy. So whereas I truly believe you obtain you know, meaningful physical information about the ocean variability from the undrogued drifters, there's a lot of processes that are basically unknown. So this is a very interesting, you know, uncertainty assessment that, you know, hopefully we need to do one day, or I'm hoping to be able to do one day, trying to understand better the behavior of the undrogued drifters compared to the drogued drifters. Because today, if you go to the Global Drifter Program database and you download all the data, you will find more undrogued drifter data than drogued drifter data in terms of, you know, the number of points. So I think that's a very interesting conceptual aspect that I wanted to bring out.
It's a really great point, Shen. Thank you for bringing it up. I presented at the Sargassum session of this workshop 2 days ago, and one of the interesting things we found there was that, you know, people were wondering, where did all the sargassum that inundated the Caribbean in 2011 come from? And when you backtrack using only drogued drifters, which was done in an earlier study, you would conclude that it would have to come from the eastern equatorial Atlantic and then further south from there. There's no drogued drifters that you would find a pathway from the North Atlantic. So the conclusion had been made that it couldn't have come from the Sargasso Sea. I showed that if you actually look only at undrogued drifters, you find indeed very reasonable pathways that would come from the eastern subtropical Atlantic. And so then the only question is, well, how did the Sargasso get from the Sargasso Sea to the eastern equatorial Atlantic if it moves more like undrogued drifters than drogued drifters? And the answer was the absolutely historic North Atlantic Oscillation event in 2009, which basically kind of flushed the Sargasso Sea out and moved it to that region. And then if following that pathway of undrogued drifters, you find qualitatively very different conclusions than you would if you only looked at the drogued drifters. So yeah, there's a lot we can learn about how Sargasso and marine debris moves from looking at that data set. And if we can recover the 15-meter velocity information from the undrogued drifters, as some studies have already tackled, then we can greatly increase the volume of data that we have. And again, this is sort of an uncertainty estimate exercise. How uncertain would those velocities be? That hasn't been done well, I believe, in studies that have been published recovering those velocities from the undrogued drifters.
One last thought, if I can. The sea surface temperature, it's a key aspect of the drifting buoy program for satellite validation. And it seems to me that the temperature measurement itself lends its uncertainty determination to a very clear metrological analysis that's best desired. And you've got there's a new effort, I think you mentioned it in your last slide, that's got a target of 0.05 C for surface temperature, which I continue to think is really ambitious, but it would serve as a wonderful example for the Ocean UQ. I'm sure Shane's thought of this as well. And so hope we can work together closely on that.
Yes, absolutely. I think that, we have a lot to learn from the measurements, which we, from tank experiments, we do believe that the newer sensors have that kind of accuracy. And with hourly observations, we're able to validate models for the diurnal cycle of SST variation, for example, that have to be used when you're doing the calibration and validation of satellite measurements. So yeah, there's a lot of exciting things in SST that Shen is definitely aware of as well.
And then one last thing I should push the host for this workshop, the Ocean Best Practice System. I would love to find a way for the drift and buoy community to make use of the Ocean Best Practice System. So I think right now most of your publications are indeed peer reviewed, published in respected journals. But if you find something there where that's not the case, but it's still a message that you'd like to, a document that you'd like to make fair without, necessarily being peer reviewed stuff, keep the Ocean Best Practice System in mind.
Thank you.
What do you mean, Mark? Can you elaborate? What type of contribution do you think the Global Drifter program could make to OBPS?
That's where I'm coming up short. If there were some practices that are in development or are clearly known as best practices that reside at AOML instead of in the repository at Ocean Best Practice System, they'd be welcomed.
It's something good to consider. I just kind of have it as my personal best practice to try to get things through peer review before we adopt them, like with the hourly location velocity and with the hourly SST data that they're working on now. We will release that once that has been peer reviewed and the methodology is public. But there are always things that are kind of being worked on, and it's good to have a venue that follows, that's not requiring that threshold, I think.
Yeah. The Ocean Best Practice System does have a relationship with Frontiers in Marine Science, so that's a peer-reviewed possibility.
Excellent, thank you.
All right, we better move on. Thanks very much, Rick. I appreciate your time and willingness. Our next speaker is Bob Heitsenrether. Shane's got a question. Go ahead, Shane.
That was not a question, it was a clapping for
I'm sorry.
It's a reaction in the Zoom application, sorry.
Thanks. Bob Heitsenrether works at NOAA's Center for Operational Oceanographic Products and Services and holds the position of lead for the Ocean Systems Test and Evaluation Program. COOPS is the Tides and Currents agency that manages the tide gauges around the country and conducts the current surveys. And Bob's going to talk to us about uncertainty and water level measurements. Thanks, Bob.
Thanks for the intro, Mark. Can everyone hear me and see my slides?
Yes.
Great, thanks. So I just want to thank Mark for including our program office in this workshop. It's very timely. We're at a point now where we're discussing within COOPS how we can improve the way we quantify our measurement uncertainty and communicate that as well. And this talk is just sort of introducing our challenge. We don't have the answers yet, but I think it would definitely be useful to sort of set the stage and share with you all what I think we do a good job at in terms of reducing uncertainty and communicating that, and where we need some improvement in defining measurement uncertainty in a quantitative way. And it's been really good to listen to the talk. So I just want to say it's nice to hear everything, and certainly starting to think about how we can adopt some of the standard terminology and methodology. So this is just an intro that I put together with our chief scientist, Greg Dusek, who's also here. So COOPS maintains the United States network of nearshore ocean observatory systems, and a major component of that's the National Water Level Observation Network. And this includes over 200 long-term stations that are throughout, Atlantic, Pacific, Gulf Coast, Great Lakes, and all the island territories. So One of the big challenges for us is the spatial coverage of that network. It's quite large, and we have systems that cover a broad range of different environment types. And we have a variety of station designs, which is sort of depicted there on the right. Some very small, simple stations where that permits, like this acoustic sensor in a well and a small electronics enclosure, to very large, robust systems like the single pilot instrument platform shown on the bottom. This is a platform in the Gulf of Mexico that stands approximately 9-10 meters above mean sea level. It's designed to withstand Category 4 hurricane surge. So in addition to the spatial coverage, we have a broad range of applications that are related to a whole range of different temporal scales and different processes. So we're most commonly known for our tidal predictions and tidal datum products. And that's part of U.S. water level datum reference system. And some other examples are navigational safety. What I didn't mention in the last slide, all of our stations provide 6-minute average real-time data that's available through satellite transmissions and online. So that's critical for the mariner that is piloting the large cargo ship and has to consider vessel clearance. That real-time information is also critical for storm surge, emergency management, and coastal inundation. Some of our coastal tidal systems are part of the tsunami warning system. They're used both for real-time information and post-event forecast validation. Water levels are important for supporting bathymetric surveys. And then the longer term records are useful for coastal resource protection, and then also the long-term sea level applications related to climate variability. So that's just an example of some of the variety of applications that our data is used for, which presents another challenge in coming up with a standard for quantifying uncertainty. So just for example, how these different timescales have different these applications that are associated with processes of different timescales have different uncertainty quantification and accuracy requirements. For storm surge, the user is interested in, where the water level is now. Is my property inundated? Are the roads inundated? How does that relate to the water levels, say, a month ago where there wasn't a storm event? And then compared to the long-term long-term sea level applications where, we have stations that go back many years, and for the stations that have 30 or more years of continuous data, that's they're used for long-term sea level trends and related analysis. Then the user is more concerned about vertical stability, vertical reference, technology transfers at that particular station over the years. So again, that's just another challenge: the spatial coverage and the variety of processes of different temporal scales that our data are used for. I also like to mention that a subset of our stations are part of the Global Sea Level Observing Network. So we're very involved with that IOC program. The acronym is GLOSS, and we are in close coordination with all things associated with the climate change. So another challenge is we have a variety of different water level sensors across all of our stations. Most of our stations, in particular in the tidal zone, include acoustic or microwave radar sensors, and we are currently undergoing a transition from the radar to replacing the acoustic, and I have another slide about that later. So the acoustic system is just a surface sensor that sends a signal down a small sounding tube that's enclosed inside of this protective well with a specially designed intake to mitigate drawdown from currents and waves. And this has been in use since the 80s. It's served NOAA quite well over the years, and more recently we've been transitioning to these radar sensors that offer a lot more advantages. They have no components in contact with the water. It's a remote sensor, less hardware, and less susceptible to changes in the transmission path. It's a 26 gigahertz signal, where our acoustic is a, I believe, 2 kilohertz signal. So there's more impacts with environmental changes such as temperature and sound speed. So part of the challenge there is, having tracking the overlap of the stations and having a smooth technology transfer and ensuring the integrity of our long-term records. So in the Great Lakes, most of our stations employ shaft floats with shaft angle encoders. I don't really talk too much about this. The infrastructure up in the Great Lakes is quite robust. We have these large concrete wells that are enclosed in climate-controlled brick houses and sumps that extend into the lake with an intake just to survive the harsh winters and all the ice cover. And then there aren't as many long-term climate applications for those particular stations, so the uncertainty quantification is less of a challenge or not as a high priority. And then at some of our other sites, we use pressure sensors as primary sensors. And at most of our sites where we have acoustic and radar, we have a backup sensor that's a pressure sensor, just to have two different technologies. And most of these stations have the bubbler pump type system, where you have the pressure transducer up on shore in the tide house. And then you have a pump system that measures the hydrostatic pressure to push a little bubble out the end of an orifice. So there are the several different water level sensor types. So I just want to point out that Co-ops puts a lot of effort into ensuring we have a robust station design to ensure reliability and long-term continuity of records. Again, there are a lot of applications that rely on that real-time information, in particular the navigational safety applications and the storm surge hazard warning system related applications. So at all of our NLAWS stations, we have two separate systems. We have a primary water level sensor, and again, in most of these stations, they are acoustic sensors that are now being transitioned over to the microwave radar, and then a backup system that is typically a bubbler pump pressure system, so another technology. So in the event that something happens to the primary water level sensor during a storm or any sort of incident, whether it's from a vessel strike to some environmental issue, we can switch over to the backup sensor to ensure we have continuity in our records. And each of those systems has an independent data logger controller and power system. And then most of our stations have two different sources for real-time communication, satellite and typically a cellular IP modem or a phone line in places where we don't have that internet connection. So the point here for uncertainty is another challenge is associated with the data processing and the derived products. So if we have a station where there's a gap that gets filled, the primary sensor goes out, then we have a gap filled with the secondary sensor, that's a different type of technology, or we have a spike or something that was removed and interpolated, then that's another level of uncertainty. And I also want to point out that Co-ops puts a lot into real-time QA, QC. With our real-time transmission, with the ingestion system on the database side, there's an automated series of QC checks that are in accordance with the Core TOD water level manual, and flags get set automatically. And also the thing that's unique about Inlon is there is a staff of human observers that are on 24/7 constantly monitoring the data. And if there's a series of flags or suspect features in the data that maybe the automated QC checks don't catch, then those systems get shut down and there's communications immediately to the field folks who can fix the problem. So again, we put a lot into that long-term survivability, reliability, and then the QA, QC. So moving on to the challenges associated with the measurement error, in particular with the uncertainty in the measurements from the sensors, which again is more of my focus. The folks that Greg works with in Silver Spring are more focused on the uncertainty associated with the analysis products. So there's four categories of measurement error that we think about, and I think that Co-ops does quite a bit to reduce the amount of uncertainty in the first three categories here, and where we really need to sort of improve upon, what we're quantifying and communicating is that fourth bullet. So we have sensor noise, the inherent sensor noise, error associated with the laboratory calibration process, which I'll talk a little bit more about. The field level surveys we conduct to have a vertical reference to land and a benchmark network, and then the stability of that. And then finally, the big challenge is, in terms of quantifying the uncertainty, is the impact of environmental variability on the sensor's performance. And again, since we have so many stations over a broad range of environments, coming up with a method for quantifying uncertainty that has some sort of standard across the network is really a challenge. And I think what Co-ops does well is we do a lot of rigorous testing, and we describe specific examples and empirical results, especially with technology transfer. And I'll talk a little bit more about that now, but that really is sort of the, what I need to point out, what we need to work on more. And we're very interested, again, in this group and the CLIVAR uncertainty quantification group. So again, I just want to thank Mark for looping us into that, and we hope that we can continue an exchange with that particular group. And I've even passed around the video that of a presentation that Shane gave introducing the group back in June, I believe, at an IOC conference. So a little bit about our lab calibration facilities and procedures. So these are primarily related to the acoustic sensor and the microwave radar sensor. So we have A couple facilities, both in, I'm sorry, I didn't mention, I'm at a field office in Chesapeake, Virginia. Co-op's headquarters is in Silver Spring. So for the acoustic calibration facility, we have we have a redundant system in Silver Spring and a primary system in Chesapeake. So we can perform tests, and anytime there's an upgrade or an issue, we can compare both of those systems, and we have the capability to, calibrate a series of sensors at both facilities and make sure we have repeatability and precision. And I have a couple references that show where we are with that. So at this facility, we have a long sounding tube that is enclosed inside this temperature controlled box with a string of thermistors. And we collect a series of measurements at short, medium, long ranges. The maximum range in this facility is about 9 meters. And that's all compared to a NIST traceable steel tape. And one of the key outcomes is getting the precise location of the sensor's zero range point, because that varies for each sensor. And then that's related to the survey point that is level surveyed to the benchmark network in the field. Similarly, with the acoustic radar sensors, our calibration and verification procedure involves installing the radar in some fixed mounts that you can see here, with a known range that is referenced again to a NIST steel tape, and ensuring that we know exactly where the sensor zero is. And in both of these lab procedures that get the sensor zero point, we check for sensor noise and ensure that it's within specification. And occasionally, I would say maybe 1 out of every 20 sensors, we do find a sensor that's noisy, and we can prevent, or it has some other issue, and we can prevent it from getting installed and causing issues in the field. So again, a lot put into the laboratory checks, the verification, ensuring we know exactly where the sensor zero is. And this also on the right, we have this outdoor range that Mark Bushnell was instrumental in the design and early installation of this. Again, for the radar sensors, looking for more applications that involve longer ranges, we have this unique target system where we can move this metal target back and forth and verify the measurements at longer ranges, and also look at things like time response compared to other sensors. So again, just to sort of point out some of the lab facilities that we have to help us address the uncertainty quantification issue or describe some error we see in the field. We also have this 2-story platform, which is unique. This is again at our Chesapeake, Virginia facility, and we have a full tide station with a couple tanks and a pump system that we can vary the levels at different rates of change. And again, focusing on water level sensors, but we also use this for integration of other meteorological sensors that are commonly installed across all of our NLON stations. So initially, several years back, this was primarily for system integration, throughput testing, or say if we had a new sensor, what's going to happen when we integrate this to a tide gauge, and what's the data going to look like. And this also was commonly used for just training field personnel on troubleshooting, level surveying, things like that. But more recently, Greg and I have been working on some projects to help us quantify some differences and understand some measurement error with the AquaTrack sensor, in particular to explain results that we're seeing in the field associated with the transition of technology. So again, this is something, it's another tool we can use, and we have higher resolution observations of things that impact the sensors. For example, we have a whole temperature string down this well. We're typically in the field at a tide station, we'd only have 2 temperature sensors, one at the top of the well and one at the bottom. So we can really think about things like how does sound speed gradient impact the AquaTrack sensor. So again, that's just an overview of the lab facility. So that's an area where I'm confident that co-ops invest a lot in reducing the uncertainty of sensors before, any uncertainty related with sensors before they go out the door, with careful calibration and verification checks. So the other thing that co-ops puts a lot of time into is geodetic leveling. I'm not going to get too into this, but it's an important component of the whole overall uncertainty quantification picture. So at every NLON station, we install and maintain a network of 10 benchmarks or little survey markers in accordance to the National Geodetic Survey standards. And we conduct level surveys at every station at least once a year, and sometimes more than that if there's a storm event or any sort of geophysical event that requires another survey, or if something gets damaged or moved. So again, this is another repeatable, highly accurate process in accordance with NGS standards that we can vertically reference our sea level measurements to land. Now, what this doesn't capture is the large scale land motion. So our benchmark network is attached, so to speak, to the land. And in some sites, we have subsidence or uplift that is not captured in these surveys. So a lot of the sea level products that Co-ops publishes are relative sea level products. More recently, we've been looking into use of GNSS and working with NOAA's National Geodetic Survey to use GNSS to resolve the vertical land motion component to get a true sea level measurement. So it's sites where NGS has a nearby continuously operating reference system. Co-ops has been coordinating vertically tying that system through level surveys to our tidal benchmark network. And then we've also just started in the last couple of years installing our own GNSS systems at co-located with water level sensors. And again, that's something that's been in coordination with GLOS. So we're working to improve that geodetic reference. So again, just sort of transition over to another thing that we put a lot of effort into is test and evaluation of new measurement systems. And so most recently, we've been focused on transitioning this microwave radar technology, commonly referred to as microwave water level sensors, across NLAN. So just a quick background, Co-ops started to use these microwave radar sensors for the bridge clearance systems that, again, were primarily focused on navigational safety, measuring the air gap so the ship pilots know how much clearance they have under bridges. And then, after success with that particular application and also watching the rest of the international sea level community transition over to this, we started to do some tests and evaluation ourselves and eventually, started to transition these sensors across the NLAN network. And this is an effort that's currently underway, being led by my co-author, Greg Dusek, in terms of coordinating all the overlapping data sets and ensuring that we are maintaining the integrity of our system. So just to sort of point out another challenge here, I think it's unique how the Co-ops does invest a lot in test and evaluation. There was actually a test plan that Mark Bushnell was instrumental in developing and implementing back in 2008. And we actually installed test systems at 7 different NLAN stations to represent a variety of different environment types. And each of those test stations had multiple sensors. So that's quite a bit. And, from that data set, I think we were well prepared to transition these sensors across NLAN and had a good handle on the error and uncertainty for this particular cases. But now with this transition, we have 81 of these sensors installed to date. So that significantly increases the sample size. And, you see a lot of different issues that need to be addressed carefully. So at all the stations where we have a radar, we have a minimum 1-year overlap with the old technology, which is typically the acoustic sensor. And at GLOS stations, we require a 5-year overlap. So there's careful analysis. There's a detailed checklist. And for sites where the differences are larger, there's careful analysis conducted to quantify the source of the difference. And typically it's error with the acoustic sensor. So again, this is just the point is that COS puts a lot of time into very site-specific analysis. But again, the challenge is how do we quantify uncertainty in some general way that applies to the whole network? And again, just want to mention that we work closely with the international community and other folks who are transitioning radar technology to ensure we're handling it all in the same way to maintain the integrity of the long-term records used for the global sea level research. So co-ops contributed to this IOC GLOS manual on radar gauges, and there's a lot of good best practices in that. So again, we know there's specific sources of error associated with each sensor. And again, we focus on very site-specific things. And I think we do a good job quantifying these things for particular cases. There's a couple good references here that talk about the sources of acoustic measurement error. And this last one was the most recent by Park et al. And talks specifically about the comparisons with the radar sensors and differences in how they're explained. And again, with the field tests, this is just an example of some data we have collected on the that test platform out back. We have this temperature string down the well, and this up here is just a time series of the differences between an acoustic, a microwave, and a pressure sensor, and all the different differences. And you can see here, we induced a temperature gradient in that Aquatrack well using some ice sheets. And you can see that with a 15-degree gradient from top to bottom, you can see that the acoustic sensor starts to deviate from the others up to 3 or 4 centimeters. So this is just an example how we can come back to our lab, generate a controlled situation to help quantify what's happening and explain it with, you know, this particular source of error, which is temperature gradient and sound speed gradient. So in conclusion, I think that, you know, where co-ops invest a significant amount of time, this would also be recommendations for best practices, is rigorous test and evaluation of new measurement technology, intersensor comparisons, and making sure we have long records of anything that gets transitioned. Lab facilities and routine calibration testing, we put a lot of care into making sure sensors meet their noise requirements. There's no additional noise or issues with the sensor performance, and knowing exactly where that zero range is. So we can relate that to the level surveys in the field. A lot of effort put into the level surveys, maintaining the benchmark networks. And now we're introducing GNSS to get even more accurate and additional information on vertical reference. And then again, we have our real-time QA, QC, and the watch staff, and that's all in accordance with the latest Quartile water level manual, robust station design for long-term survivability, and then a good record of that long-term measurement technology transition. So most recently for the radar, for every station, you know, aside from a few things where you know, the legacy system gets damaged by a storm, it has to get moved for construction. At most of the sites, we have that long-term overlap and a thorough explanation of differences that are quantified. Now, where we could do a better job is improving the water level measurement uncertainty quantification over that range of applications. The current specifications that we have now on our websites are based on known sensor resolution and accuracy that's based on a series of empirical results, limited lab and field tests. So again, this is just something that at the program office level, we've been encouraged to pursue a project. And again, Greg and I are just starting to get our thoughts together about how to begin this and what folks and contributors we're going to need. So again, it's very timely to be involved with this particular group, and hopefully we can continue the exchange. So I think I kind of covered this through the talk. The challenges of, you know, coming up with improving uncertainty quantification across NLON. We have spatial coverage, a range of different applications involving different temporal processes, 4 water level sensor types, the difference between lab verification results where you have a controlled environment and favorable targets for the radar, you know, a flat metal sheet, and then moving out to the field, and then publishing verified products that might include some edits and backup sensor fills and processing errors, and then finally the communication and perception. Although co-ops is very confident in the products we put out there, I'm sure everyone else has the same issue. As soon as you sort of open up about uncertainty, then some folks that might not understand the science applications could misinterpret it. So for future efforts, again, there's a lot to be done. Hopefully we can come back and report to this group when we're further along, but some initial efforts involve increasing ancillary measurements of NLON stations. We've talked about maybe more temperature profile measurements in acoustic wells, CT sensors near pressure sensors, so we can quantify the density that introduces uncertainty when you convert from pressure to the actual water depth. We've talked about maybe developing a coastal classification system. If we could sort of summarize, several categories environment to cover NLON. And then I think we can do more to leverage the results from this radar water level transition. We have, a 1-year overlap at every single station, at least, where we're transitioning the radar. A lot of folks monitoring that and explaining differences. So I think that could potentially be leveraged to have a more general or higher level uncertainty quantification. And that's all I have. So glad to hear people's thoughts, questions.
Thanks, Bob. Really appreciate you and Greg thinking about this and participating. Questions for Bob?
This is Christoph. I have a question to you, Bob. What I learned from the presentation is that you're trying to get the highest quality water level data that is possible. The question is does it happen that people are coming back to you and say, all right, here seems to be some inconsistency in regard to some data product that they develop? And if yes, if this happens, how do you deal with that? So that data users who seem to be not happy with the data that they are seeing.
I think, and I'll let Greg fill in if I miss anything. I think that most of our issues with unhappy users are more related to reliability. So if there's a station that goes out every time there's a storm, we hear from the pilots. Where's the data we need to go in? As far as the accuracy, you know, we've only had a handful of situations where there's a research application where, you know, I think a couple issues have been with the uncertainty associated with the acoustic sensors temperature gradients, and at a couple stations there, you know, there's obviously some errors associated with periods where you have a bigger temperature gradient in the well. And then, you know, we just provide more data, and they're usually, you know, internal users. So within co-ops, we have users of our own products. So often it's communication between the folks doing the oceanographic analysis products and, you know, the folks doing the engineering. So I can't really think of too many specific issues with an unhappy, you know, climate researcher, but a lot of questions get asked about uncertainty, and I think we could do a better job answering. So Greg, do you have anything to add to that?
Yeah, I'll just add, you know, I think it's almost the other end of it where, you know, there's some cases where we want to be able to say, particularly for data that might not be kind of our standard NLON quality data, how accurate is it? And thinking about partner data in particular. So we have cases where we work with partners like USGS now and others to potentially utilize their water level data, which might not be always collected at the same standards as our long-term NLON gauges. But just because it might not have the same level of uncertainty, it doesn't mean it doesn't have any value. And so I think being able to quantify those cases where, you know, might not be the best water level data you can collect, but it's still useful for some applications like storm surge, you know, model verification or something, or you know, maybe not long-term sea level rise, but something else. I think understanding the uncertainty to be able to establish, you know, when the data set meets certain levels of quality, I think is really helpful for some of our users. So less our long-term data at kind of our standard NLON gauges and more kind of, you know, one-off observations or, you know, short-term observations or partner observations, things like that.
Yeah, thanks for adding that. So yeah, you definitely have a lot of partners who come, and with that robust station design I showed in the little block diagram, there's a cost that comes with that. So we have partners that said, hey, I don't need that full-blown NLON station. I have this sensor that's lower cost, and I want to use it for these applications. And, you know, where does your accuracy requirement come from? So that's really, you know, another big challenge that Greg pointed out is working with partners who might not need and may not, you know, be able to afford a full-blown NLON.
Thank you.
Other questions?
Yes, I have a quick question. Thank you, Bob, for your presentation. I'm very glad to see you doing a lot of work, and it seems to be a lot of work to do to conduct all of that. So I think I think I understood you moving from an acoustic system to a radar system, maybe because that allows you to reduce uncertainty. So are you able to tell us by how much you've reduced, you know, like the total uncertainty on sea level moving into a new radar system compared to an acoustic system?
So yeah, I think there's a couple big motivating factors. One is just the simplicity of the system. You know, it doesn't have all the components, so there's a cost, and it's easy to install, and there's, you know, less hardware. And there is a lot of potential to reduce uncertainty because the 26 gigahertz signal won't be impacted by temperature and other things that the acoustic signal will be. So I can't put out a blanket statement, but I can say that in some particular cases where you have higher temperature gradients, and that's becoming more of an issue because there's a growing requirement to elevate our platforms. So we want, you know, some of our stations to survive Cat 4 HRMs. So in some of the sites where we have longer wells that are becoming more common and higher temperature gradients, the difference between the radar and the acoustic sensor can be as many as, you know, a few centimeters during that particular event. So I think that's the biggest, and there's some other periods that we're taking a closer look at, but with the temperature gradient, it can be a matter of a few centimeters. that you include.
So you're telling me that, you know, on 6-minute averages, you can have differences between one system or the other of several centimeters in the water level?
Yes. And then just a quick, I'm sorry, I kind of was concerned about the time. So you can see here, this is the difference between the radar and the acoustic sensors in blue here. So you can see this is in our lab facility, controlled environment. When we induced the temperature gradient of 15 degrees, which might be a little extreme, you could see on this relatively short well, just a few meters, which is half the size of some of the wells in the field, we get a difference of 3 centimeters in this particular case.
Oh yeah, you showed that slide. Does GLOS have a uncertainty requirement for 6-minute water level?
I believe they do, and I would have to check on that, but I believe they're more focused on the long-term uncertainty. I know there's definitely requirements for monthly and annual averages, and there's a couple studies that actually show some of those seasonal and daily temperature-induced gradients just average out over time. But I don't know if they have a requirement. I'd have to check for 6-minute, but I know they have requirements for monthly and annual.
Great, thank you.
Sure.
Other questions? One of the things I'd like to mention is that Co-ops runs an acoustic and a microwave device side by side for a year or years in order to validate them. And there was an instance in a harbor in New York where they had to relocate the station, and so they deployed a microwave. I think it was a few hundred meters away from the primary acoustic one, and they couldn't get them to match. And in the end, it was found that it's an actual real-world difference of a few centimeters just across this short distance in the harbor, and it's kind of the representation error that Kyla was talking about yesterday. I don't know, maybe you guys want to mention that or add to it.
Yeah, no, I was actually thinking about, I know Mark, you and I discussed that, and it was interesting to see Kyla's presentation, and I was thinking about representation error on smaller spatial scales than what she had described. And I thought that was pretty interesting, and there's definitely some, analogous things. And even in particular when you have, so that was a case where you had the stations separated a little bit. So there was something that was, the true water level varied that much, and it was out of spec. But even sometimes when you have these sensors side by side, and for example, you're in an open ocean environment where you have a lot of wave energy, and the acoustic sensor, is measuring the sound reflection in a little 2-centimeter sounding tube, and the microwave sensor is, measuring a big patch of the open ocean. You can get those same sort of representative errors, uncertainties rather, on smaller timescales. So yeah, I definitely thought about that sort of terminology and that explanation that Kyla described. It relates to some of these situations on smaller spatial scales, I think.
Anyone else? I can keep going on this all day. I had an epiphany during your talk, Bob, and because I'm so familiar with water level measurement technology, and I'm thinking about the acoustics and the microwave. There's two schools of thought on determination of uncertainty, quantification of uncertainty. The first is the classic metrological approach as described in the guidance for uncertainty measurements. And then there's the less desirable top-down approach where you just treat everything as a black box and establish a measure of uncertainty that way. And so I came into this session with this binary thought, it's got to be one way or the other. And somewhere through the middle of your talk, I realized that in almost every instance, it's going to have to be a combination of the two. It's pretty easy to do a strict, uncertainty budget for an acoustic sensor, but who knows what's going on inside that microwave sensor, right? You have to treat that as a black box. And so the epiphany is that what gets treated as a black box is a level of granularity that one must accept. At some point, you have to just say, beyond this, I can only go with the top-down approach. What are the uncertainties I see or the vendor provides for this particular instrument, and then you build upon that. And I see Stefan's here, and I'm betting Christoph has some thoughts on that idea.
Okay, if I may start.
Please.
Yeah, this is a very good idea that you brought up. And the first thought that went to my mind is you need to have the experts involved in the evaluation of the uncertainty. So if you're not an expert, you have to see that as a black box and do some rough estimate. But as soon as you are interested in more details, if you want to lower the uncertainty, then you need this expert knowledge. And this is my view on those things. So both approach that you mentioned are okay. So it will be a good start anyway. But as soon as people worry about, the large uncertainty, then you need to have expert like you, Mark, involved, or Robert, to evaluate in more detail what's going on. That's my view on those ideas.
Yes, I would say, well, this is really a difficult question. I mean, to my understanding, or as a metrologist, I would always say that the bottom-up approach is the better one because you have better control about the uncertainty contributions that might be or are necessary to consider. So I would always say that it's the more reliable one. On the other hand, I also see that there's, of course, a kind of practical need, and you cannot always do the bottom-up approach because you simply do not have all the necessary information available. Then, of course, you have to look for other methods, and then the top-down approach is, of course, the one that you can take. At the end, it's always a kind of trade-off. Okay, you have to see how much uncertainty in the uncertainty you can accept in a bottom-up, in a top-down approach, and how much efforts you are willing to spend in a top-down approach. And this has to be, as Christoph has mentioned, actually decided by the experts.
Another advantage to the bottom-up approach is that as you identify the elements in the budget, you can work to decrease the uncertainty of those particular elements. Any other thoughts? So I've in the chat box, I've put the location of the presentations and the location where you can obtain the recordings of these sessions. And I think we've got about a week before we complete a session wrap up. So I would urge anyone to contribute any thoughts or papers they may have that might help us with this. All participants can place things at the same location where the presentations can be found. That's the session Google Drive. And one last chance, anybody?
Mark, just as an idea, so could we also come up with some sort of questionnaire or something? Is this a good tool for the summary, session summary, that we would ask all participants to respond to some specific questions?
Excellent idea, Christoph.
Okay.
Mark, one further suggestion. Listening to a wide variety of talks, many of them quite outside my immediate knowledge as a chemical analyst, I don't think that everybody is always using individual phrases or words to mean the same thing.
Exactly.
The phrase quality control, quality assurance are classic examples of where that's certainly true, but a variety of others as well. I think some work thinking about an appropriate glossary so that at least people recognize there are a series of different concepts, even though they might sound like superficially as though they ought to be the same.
It's an excellent point, Andrew, and I'm thrilled that you were able to join several of our sessions. Thank you very much. The first thing that comes to mind, and I think Christoph can probably identify it better, there's a vocabulary for instrument metrology or something.
I think Stefan is the expert for that. this vocabulary?
Yes, there is indeed available vocabulary of metrology, okay, which is simply called the VIM, V-I-M, okay, and this is available at the BIPM webpage. But as I've mentioned, it's of course designed for typical metrology questions. So, but nevertheless, it's not necessary to invent the wheel new. So what can be taken out of this, okay, should be taken out of this because it's in the meanwhile accepted in a variety of areas. What I just want to mention is still it's not so much the words, and at the end I wouldn't care if something is called measurement uncertainty or error or accuracy or whatever, okay? It's actually the concepts behind we have to agree on which are important. And once we have agreed on the concepts, what is uncertainty supposed to mean for someone, okay? Then we can find the word at the end anyway.
I would agree that that last part that Stefan just said then is the important part. I think that the difficulty is that different parts of our community have different concepts that they have as their prime concerns, but they tend to use similar sounding words to talk about them. You know, when you talk about the quality control of data, it certainly bears little resemblance to the phrase the quality control of chemical measurements.
And this triggers another thought I had earlier this morning. Someone pointed out that each of the EOVs has a 3 or 4 page document associated with them. And in there, it expresses the desired uncertainty and the realized uncertainty using today's technology. And when you look at it, it's expressed as a percentage, and there's no further details. And so, in fact, you don't know what it is they're stating is desired or actually achievable today. And there's a section below that for definitions, and there's no definition there. So, you know, these are documents from the Global Ocean Observing System that I think are missing the target. So, Andrew, you're exactly right. The terminology is not adequately used across the entire spectrum.
And I think that Stefan's comment, which is clarifying the parts we think of as important concepts, is clear, and you're exactly right. You know, the distinction between uncertainty and relative uncertainty is quite striking if you go over a wide range of values.
I think, if I may add to that, I think everybody's right in here, and I think some of the issues with the EOVs, you know, the Global Ocean Observing System, is actually, if you look at the documents that frame the Global Ocean Observing System, the Framework for Ocean Observing, that's the name of the document, or if you look at the GOOSE 2030 Ocean Observing Strategy, even the concept of uncertainty is completely absent from these documents, right? So I'm trying not to be too harsh on the critiquing those documents, right? Because they're very useful and valuable, and they propel us, you know, forward in observing the ocean, or modeling the ocean, or thinking in theory about the ocean. But the concepts of uncertainty are completely absent from these documents. So I think it is the role of, you know, this group, the group US CLIVA that I'm co-chairing. We're trying to have this, you know, cultural shift, trying to, you know, bring forward those concepts. Because once those concepts are in those documents, then we can get appropriate requirements for uncertainty, and then people will start thinking about it.
Yeah, just to follow up on that, I think it goes beyond that, because listening to all these talks, some people use the true value meaning the result of a model, where other communities use the true value as the result from some instrument, right? So what is the norm? What is the true value that the uncertainty is measured against? That's something that also needs to be defined.
Yeah, and that was echoed by, you know, I think like Stephen in the talk on the first day talked about, the uncertainty is only useful when you're trying to do comparison, right? So when you compare in situ to model data, if you don't have an estimate of the uncertainty on each value, on either of those two values, then you can't do anything about it theoretically. So
Absolutely.
But just to conclude, I think I'm optimist that just because we're having this discussion between several different groups, I think we're doing a good thing and we're moving forward with this endeavor.
Yeah, I hope we've made a little dent in this workshop.
So can I make another comment? So I think it's very important to keep this discussion on the terminology light. If you start to dig very deeply into the semantics of this international vocabulary of metrology, then you end up somewhere or nowhere. And so I think that's what Stefan actually was raising. Don't try to keep this vocabulary light. Don't try to define everything. So just a basic number of terms so that we can understand each other. And I think, was it Kimberly who started to work a little bit on that? So have a very light description of accuracy and reproducibility. I think I like this a lot. Everyone is understanding a little what we are talking about, and then we can refine it in another step. So.
Well, along those lines, what do people think of the idea that even if an under-resourced observer just says, here's what I think my uncertainty is, and explains how they came up with that number, I would think that's better than nothing at all, even if you don't have a rigorous quantification. Would you agree with that?
My comment there would be that up to a point, I agree with it. Certainly, having an uncertainty statement is a good thing, and understanding how it was arrived at helps one to judge how good a thing it necessarily would be. But I think we also need a little bit more guidance as to quite what is expected as an uncertainty, so that when people try to come up with it, it's done in a way that on the whole could be sensibly defended.
Which gets back to one of Stefan's suggestions for a overarching outcome of this, that we create a best practice for creating uncertainty.
Yeah, and the different estimates should be consistent, right? Because as we discussed in previous days, this is a pipeline, right? A measurement or a process may be used tomorrow for something else and then for something else, and each of the different segments of the process will add into that uncertainty. And unless it's completely understood what the previous steps were how they were done, then it would be useful to move forward. Otherwise, there's a point that it starts meaning nothing, right? The sense of uncertainty starts being lost in the process.
Yeah.
I would just second what you said about having a clear process, but I think the way to make it clear is probably to have some particular examples from rather different needs that implement it, so that people not only get to see what they should do, but if it's something that they kind of understand, to follow through how it was done, so they can think about how they would do that for something different.
And the carbonate group, I think, is quite capable of doing that in the fairly near term.
Yeah, we're looking at that particularly for measurements on discrete samples, but as you have made clear in these talks, it becomes significantly more involved when you're trying to make equally defensible statements about the likely uncertainty of information retrieved from an autonomous sensor that has been out for some months.
Yeah.
So ours is the simple case, I guess is what I'm saying.
Yes,
But I do agree that, oh, go ahead, Stefan.
yeah, I agree. Of course, this kind of uncertainty is, or a single sample that you have in a laboratory is much easier to calculate and to estimate than other quantities if you have large spaces and maybe unstable environments and so on. But what we always have to be aware at the end, okay, there is a number, okay, and the number is supposed to mean something to somebody. And the uncertainty is more or less what is giving you the reliability with respect to this meaning for this somebody. And this is more or less the target, or the what he, or he might have a target of some kind, which must be met in order that this quantity is useful for him. So what I've tried to explain is that the definition of the quantity, okay, what does this number that we produce, no matter if it's directly the measurement or if it's the product that has been gained from a lot of measurement, the number must mean something. And what does the definition, or how exact is the definition in order to catch this meaning? And the uncertainty will always be related to this, no matter what quantity it is. You can even have an uncertainty of counting fish, okay? Because it is a number and it's supposed to say something. It's supposed to say the number of fish. And if you're doing the calculate or the counting of the fish, you will also have some kind of uncertainty unless you can count each individual fish, okay? And that's, I think, the heart of the uncertainty. And then this is, I think, really some common ground for any quantity, for any area of research, okay, to be very aware about the definition of the quantity and what you want to say with this quantity, because it actually defines the target uncertainty that you actually want to meet at the end.
I think that's a very good point. Thank you, Steph.
Well, for some reason, I'm signed up for another cafe at 7 a.m. in the morning tomorrow, Eastern time. And it would be quite easy to peel off from the foyer or whatever it is in the cafe and further this conversation. We're already half an hour past the time, and I appreciate everyone sticking by here. So again, still plenty of opportunities to send us input. Thanks everyone for your participation. Very, very informative and then enjoyable. Let's sign off now.
Thanks, Mark.
a lot, Mark.
Thank
Thank you very much,
Bye.
Mark.
Thanks, Mark.
Thank you
Bye-bye.
very much. Bye-bye.
Bye.